Friday. I have to say, this room just feels more and more dingy as the weather outside gets better. Depressing to be in here. It's nice outside. All right, so today we're going to sort of continue the grab bag part of the class by talking about performance. So we kind of had a nice segue to this last time when we talked about different kernel designs, right? Because we sort of introduced this trade-off between making design choices about how kernels should be put together and the performance implications of those design choices. So today we'll talk more about, that word just never looks like it's spelled right to me, performance. I think it is spelled right. It's performance and benchmarking, right? These two things are kind of very, very sort of closely tied to each other, right? Okay, so we started returning the midterms. If you want yours, come to Davis 303 after class. I think Scott's there till 5 today, so pick up your exam. As I posted on Piazza, we are not going to accept immediate complaints about your midterm. Yeah. No. Yeah, there's a page on the website where it says your name and then your grade, right? No. For last year's final, we did something where we actually allowed you to get your scanned, graded copy through the website, which we will try to do again this year, right? It's a nasty, disgusting hack. But the statistics, so we'll talk about the exam on Monday. I could have done it today, but didn't have time to get the slides together. So on Monday, we'll have a few minutes where we go over the exam results and talk about them. But if you want to put your results into context, statistics for all the questions are in the solution set. Have people been able to see this? Yeah. Okay, yeah. So for each question, we have statistics, how many people answered it, blah, 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 right? So that's what we meant, right? As well as the solution set also contains exactly the number of points that you got on every question, right? Just as a representative student, right? So next week, if you have a problem with your midterm, come talk to us. Yeah?
Are there statistics for the board exam?
Yeah, on the front page. Yep. So next week, the only part of the exam there aren't statistics for are the multiple choice questions, because I just don't really care that much. It's time for it. So I will tell you that everybody got credit for the first multiple choice question. Right. So if you have a problem with your grade, come next week. The reason why we're not doing this today is because there's no way that you would have time to look at the exam, look at the rubric, figure out what was wrong with how we graded your question, and come talk to us today, right? So by the minimum amount of time that take will be over the weekend, so you can start doing that on Monday. And finally, you guys, I've received like repeated emails from some people. Like, I do see those emails. I haven't been able to respond to some of them yet, but I will catch up over the weekend. So those of you guys that are waiting for various things to happen, all of your prayers will be answered, right? On Easter. No, actually, probably tomorrow rather than Easter Saturday. All right, any questions about what we talked about last time? A couple of things. I actually want to go over the interface part a little bit more. We didn't talk about that, but any questions about the OS structure? Multi-kernels, microkernels, Adam?
So what was the kernel type that Linus didn't like, the name of?
Hybrid.
Hybrid, yeah.
Yeah.
So is there any actual difference between a monolithic and a hybrid kernel, besides better organization?
I don't know. Yeah, I mean, I think that's the problem, right? If you can't answer that question, then maybe it's not a real thing, right? So yeah, that's the assertion, is that a hybrid kernel is a more well-organized monolithic kernel. Although, actually, if you look at the layout of Windows NT, for example, they did have this weird. So Windows has this unique problem, which is, because they've been the dominant operating system for a long time, where they're actually forced to support old versions of Windows, right? Which, as Windows has progressed, are almost like a whole separate operating system that they still have to support, right? So I think Windows actually, to some degree, has almost what exokernels talked about in terms of implementing some of these things in user libraries, but it's done for compatibility reasons, right? So these compatibility layers you can activate. So they don't get angry phone calls or telegrams, I guess, from like the people who are still playing like the cool game that they downloaded for Windows 3.1 or whatever that doesn't work anymore on Windows 8, How dare you stop supporting this 30-year-old piece of software? I heard this apocryphal story once. I don't know if this is true, but I mean, I think it's likely that things like this are true, that at one point Windows had fixed a bug in their memory management logic that actually caused some old programs to fail, like old games. There was a bug that involved freeing things twice. So apparently it was safe for a while to free memory twice on Windows, right? Nothing bad would happen. So they fixed that bug that broke a lot of things. And so rather than breaking those old games, I think SimCity was one of them or something like this, like old versions of this, right? And again, I shouldn't say this on camera. Maybe it's not true. Well, whatever. I mean, somebody will downvote. Everyone from Windows can downvote this on YouTube if they don't like what I'm about to say. But apparently, they actually looked at the name of the executable, and if the name matched certain patterns, they would emulate the old behavior, right? Sweet. That's working. Yeah, exactly. If name equals OregonTrail.exe, then enable Windows memory management 95 features, like brokenness. Anyway, again, who knows? Who knows if those things are true? But I mean, it's very difficult to support software for as long as they have, and that's actually quite an achievement. So some of that may be why they're calling, or they wanted to call sort of NT a hybrid kernel, because it had a little bit of the the microkernel features and having some stuff done about the OS level. All right, so who remembers? This is a good exam question. I mean, what was the goal of, if you could think about it, the microkernel movement? What were they trying to accomplish? Yeah, Doug.
Have a more flexible kernel.
Okay, so that's actually true. That was sort of that was a result. That would be a result of a microkernel design, because the more you do at the app level, the less you have to do in the kernel, and so the more you can change easily. But what else? Yeah. Well, not just device drivers, right? What else?
Have a safer kernel by having a little stuff running.
Yeah, so minimize the kernel, right? Take the kernel, which, kernel, small thing, right? But, the kernel got bigger and bigger, and then it was kind of a nut, right? And then it was looking more like a fruit, perhaps. It's like I guess it sprouted, it became a tree. What do kernels do? They pop, I guess. Well, pop. You want to sort of unpop it, right? Get it all back in there, and then that will make it smaller, potentially safer. And so this was all that was supposed to be done in the kernel, right? Only the things that you really, really absolutely need a kernel privilege to do, right? And then everything else we would toss up to user level and implement that as user level processes. So in theory, these could fail. But this also required much more structured communication between all the parts of the system that before had just been allowed to talk to each other directly using function calls, right? So this we didn't talk about as much, so I want to go over this. And a lot of you, how many people associate the word interface with Java? Yeah, I'm sorry. This is a sad legacy of your computer science upbringing, right? And I don't take any credit for that, right? But interfaces are, really doing good system design is really all about interfaces, right? And the microkernel story has a lot to do with how you design interfaces between components of a system, right? So good interfaces in general, and this is just a little bit of a nugget before we go on today, they allow you to make, and then this is something that's actually also very relevant for assignment 3, because as I said before, unlike assignment 2, assignment 3 has a lot of internal interfaces that you guys are going to have to build, right? You have to design your core map, right? There is no standard interface to the core map, right? You can design it however you want, as long as the rest of the system works. Right? I guess there is a little bit of one, but for the VM layer, doing lookups to your page tables, all that stuff, it's yours to design. So a good interface, first of all, allows programmers to make correct assumptions about how other parts of the system will work, right? It also allows, but at the same time, it allows the underlying implementation of an interface to change and to improve. That's the whole idea, is that I build an interface, then things can use that part of the system, but that part of the system can also change and improve. I can choose a better algorithm to compute the length of a string, right? I don't have to change everything that calls strlen from the C library. I just implement the algorithm in strlen itself, and then all of your code gets a little bit faster, right? And then it also allows you, because of number one, right? Because you know what the module is going to do, it allows you to separate things into pieces that you can test independently from each other, right? And I would really suggest you guys do this for assignment 3, right? I mean, to some degree, we've given you some unit tests for certain parts of the system, but you don't have to consider them to be exhaustive, right? You can write your own. I mean, KMalloc 2 is a pretty good test of the core map, but you can write your own core map test, right? That sort of bangs on whatever interface you guys decide to implement and gets that to work, right? If you guys, some of you guys did this for assignment 2, right? Where your approach was, let's build everything, right? We'll just implement everything, and then we'll start testing, right? Nah, not gonna happen, right? Please don't do that for assignment 3. It's too much code to write. It's too complicated. Wow, I was just saying this stuff. It's like I wrote these slides. All right, any other questions about interfaces? All right, but let's talk about performance, all right? So why do we care about OS performance? Why does it matter? People are laughing, right? Yeah, okay. Yeah, so the first thing is that people prefer that their operating system, we've mentioned this in the past, be really, really fast, right? So I'll just do a little straw poll here. How many people would be happy if their system never crashed, but it was 10 times slower than it is right now? Really?
It's pretty slow already.
Okay.
So my loss is kind of marginal.
Yeah, exactly. I was hoping it was so fast that you didn't care. But Doug has a different type of problem, right? Yeah. So.
It's a server.
Yeah, even if it's a server, right? What's that?
It all depends what you do it.
Yeah, it's a good point. But actually, so this is also an interesting point. If you think about the way that we've designed large cloud data centers and a lot of the distributed systems that you guys might be learning about in that class, right? The machines fail. We've just sort of come to assume that, right? I mean, every time you do a Google search, there is some percentage of their machines that are down, right? And you don't notice unless you scroll to like the 10,000th page of the search results, right? And you're like, oh, that one's missing from last time, you know? But no one does that, right? So nobody notices, you know? But again, Google search, and this is part of what sort of launched Google's approach to doing lots of different things, and it doesn't always work for everything. But for search, it's like, you know, you can set up search that a lot of machines can fail, and your results are still correct as they need to be, right? So correct that nobody will notice, right? Because I don't know. I mean, I'm sure there's statistics about this, but my guess is that more than 90% of Google searches stop at the first page. I mean, I know more than 90% of mine, probably more than 99.9%, right? If I don't see it immediately, then I just try a different search. This is awesome. So this is a little piece of computer science lore. This is the description of an operating system. And this is a part of a paper that was written about it. It says, we have found it is possible to design a refined multi-programming system in such a way that its logical soundness can be proved a priori, and that its implementation admits exhaustive testing. The only errors that showed up during testing were trivial coding errors. How many people have committed a trivial coding error? Okay, yeah. Occurring with the density of only 1 error per 500 instructions. That's pretty impressive, I guess. Each of them located within 10 minutes, right? Classical inspection at the machine, and each of them correspondingly easy to remedy, right? Does anyone know what operating system this is describing? Whose voice this would be? So this is Dijkstra. This is the operating system, right? This stood for something, I can't remember what it was. And this was like from the 1950s. So this is a very, 1965, right? Edgar Dijkstra. And we've talked about this before too, which is that, you know, so this was one approach to designing systems, which is we're going to prove them correct, right? This worked in 1965, right? And this system, there was something I read once that the microprogramming system took several days to boot, right? So that wasn't a super. It may have been refined. But it was slow. We've mentioned that if your system rebooted instantly, maybe you wouldn't care about crashes at all. Right? So that's a performance safety trade-off. All right, so now I've convinced you we care about performance, and this is not hard, right? I mean, you guys know how to improve performance of computer systems, okay? You know, it's pretty simple. You measure the system, right? That's not hard. Analyze the results. It's straightforward. You improve the slow parts of the system. That's usually a pretty obvious thing to do. Drink your celebratory beer. And then you start over until, well, I don't know. At some point as you get through iteration 4, it's not clear that you can really get back to 1 safely, right? All right, so on Monday, we will talk about virtualization technologies, right? No, not really. Yeah. It's not that simple, right? So again, I mean, you actually packing up. That was awesome. I just gave a 10-minute lecture. Yeah, you shouldn't let me get away with that. I might start trying. So what's hard about this, right? I mean, measuring the system, right? How should I measure my system, right? And what should it be doing, right? Measure doing what, right? Analyze the results. Oh no, now I have to do statistics, right? Telling you, not in, a lot of us are here because we weren't good at math, right? That's why we're not a physicist or a mathematician anymore, right? I know that's why I'm here, right? Computer scientist, home for stupid physicists for decades. So improving the slow parts, right? So how do I actually improve those parts? And what are the slow parts of my program, right? How do I identify them? Yeah, exactly. Okay, so this one I can give you guys advice about. But yeah, okay, yeah. So let's talk about some of these challenges on a one-by-one basis, right? So measuring your system, okay? You would think this would be easy to measure time. Okay, so we're just trying to make this as basic as possible, right? Let's measure time, right? We're going to measure the time it takes the system to do something, right? That seems like it would be kind of a primitive that we would need to measure a lot of other things, right? Certainly performance, right? Yeah, okay, now here we are where we need hardware to help us, right? So counters that you implement in software may not have enough resolution to actually measure the things you're talking about. Remember, we're talking about an operating system here, right? This is not your dog slow Python script that takes 5 minutes to run, right? Some of the things that operating systems do are done like that. They have to be, right? The context switches, I mean, you're not, some of the things you would use to measure that would be like, that took 0 time, right? It's like, thanks, I know that's not true, actually. It's encouraging. And then the low-level hardware counters that you might have access to on a machine now get very, very machine-specific, right? So one machine counts at one rate, another machine counts at another rate. There's some gnarly software libraries to help with this, but this is in itself a simple problem, right? And then you have the wonderful world of rollover, right? Which sadly these libraries end up having to deal with, right? Which is that counters flip over, right? Counter runs out of space, and then it goes back to 0, right? And if you don't measure things, if you don't account for this, then you start to assume that things took negative time, right? That would be awesome. That would be a very fast system if it could do things in the past. But most systems aren't that fast, right? So let's assume that we can solve these problems. We have some sort of library that helps us measure time, right? Now we want to perform repeatable measurements, right? But here's the problem, right? You're trying to measure something that's happening right now, but your system is adapting to what's happening, right? This is sort of like the quantum uncertainty principle, right? And this is so this is one of these. There was a period of time during which people wrote papers about operating system performance, and essentially, the joke was whenever there was something on a graph that you couldn't explain, right? Cache effects, right? There's some cache. I don't know. It warmed up. It cooled off. Something happened, right? Like that's what created that outlier. That's a factor of 10 off from the rest of our results, right? So people did this for to get rid of these experimental anomalies, but a lot of them were just really a function of the fact that it's very, very difficult to repeat some of these measurements on the system. It's almost never the same way, the exactly same way twice, right? All right, I said that. And another problem is that measurement tends to actually affect the system, right? So this is a common problem with companies that try to maintain server software, right? Is that the client will come to them and say, well, I had this bug, or the system is having a hard time processing this certain kind of query. It's taking a long time, right? And so would you like to work for the company where your response is, hey, why don't you turn on all this instrumentation that's going to make it slower, right? And it's going to make it slower all the time, right? Just so we can catch these events. The other thing, and you guys have probably experienced this when you've been working, how many people here have done printf debugging in this class? Don't be shy. It's OK. Yeah. How many people have done that, and then the problem they were trying to observe went away? Yeah, because guess what? Printf does stuff, right? It's not like magic. The characters just appear on the terminal, right? Like, it generates interrupts. It creates context switches. So yeah, you're like, oh, wow, I found this bug. I know exactly how to reproduce it. I'm going to put a printf there to see what the value of the variable is, and then maybe you should just leave that printf in there, right? And the user probably won't care that their computer's just spewing printfs to the screen all the time, right? You know, as long as it doesn't crash, right? And the other problem is that measurement creates noise in your data that you have to subtract out, right? So whatever the results of the measurement are in the system, you need to have some way to factor those out. And like I said before, people may not let you measure real systems, right? So it's kind of like even my vintage of computer scientists sort of long for the, I don't know, I used to think about sort of like the wild, wild west of computer science. So it used to be, for example, that there were entire computer science departments that were running experimental distributed file systems that everybody used and put their actual files on, right? So it was like, I have this new version of NFS. Where am I going to deploy it? My department, right? It's so cool, right? It's like, wow, hey everybody, I have this new feature. Like, you know, well, only 1% of the time it kind of destroys your data, right? But whatever, let's test it here in the department. No one does this anymore. It's very sad, right? Now I get angry emails when we like set up an access point in my lab, right? And the CIT people are like hunting for these rogue access points on campus. Like, a laser is going to come out of their actual access point and destroy the one on my desk. So anyway, so we're living in a little bit more of a even in a place that's supposed to be about experimentation, we're living in a little bit more of a lockdown universe. That's understandable. People want stuff to work, right? But this is certainly true in business, where their business is not to perform computer science experimentation, right? The business is to do some other thing, and you want them to run something that's slower in order for you to help them understand their problem, their performance problem, right? Yeah, operating system. This is kind of there's actually, I mean, a lot of modern operating systems have a lot of instrumentation tools built into them, but sometimes you have to be a lot smarter than you have to be on other systems in order to do debugging. So, for example, let's say you wanted to measure the performance of something like the page fault code, right? How often do you think that code runs? It runs a lot. So you put some instrumentation in there, even if you're not doing printfs, right? If you're doing something smarter, it can still, A, generate an enormous amount of output in a very short period of time, and B, slow down the system quite considerably. All right, so now let's say, okay, well, doing measurements on real systems seems difficult, right? What are our other options, right, if we're trying to understand system performance? Right? There's a couple, right? One is we can build a model, right? And there's a whole type of person who really loves this, right? Because once you have a model, then you can do mathematical things to it, and you can prove things about it, and you can just, you abstract, again, you abstract away all the low-level details, the stuff that I think is interesting about the problem, and then you can manipulate it by just moving variables around. The other thing that is actually an approach that computer scientists actually do take a lot is to build a simulator, right? So I can build a simulator, and you can build simulators with a variety of different levels of detail, right? But a simulator is a piece of computer code that's designed to simulate the behavior of some other thing, right? So for example, Guru's been doing a lot of work with a simulator that actually simulates an entire computer architecture, like another chip, right? You can actually use that simulator to boot an operating system, right? The simulator is actually simulating every instruction that's being generated by that processor in software, right? How long does it take to boot Android with the full image? Like 2 days? Yeah, so it's slow, right? That's one problem with really detailed simulators, right? Is that you're talking about like a factor of 1,000 slowdown, right? Which when things are fast, you don't care about. When you're talking about something that took 10 minutes on the real system, yeah, so it starts to be a problem. And if you're ever wondering if you're dealing with a model or a simulation, it's pretty easy, right? If you see equations, you have a model. If you see code, you have a simulator, right? And it's not real code, right? The models and simulations both have drawbacks. I mean, obviously, we'd like to measure real systems, but we talked about how hard that is, right? So if you use a model, the nice thing is in many cases, if you abstract away enough detail, you can actually start to prove things about your system. The problem is that usually by that point, you've made a bunch of really ridiculous assumptions about how the system works, right? So for example, in wireless networking or in sensor networking where I used to work, there were all these routing protocols that started off by saying, assume that every node can communicate perfectly with all nodes within a certain radius of it, right? And you were like, that's not actually at all true, right? So all of the other 10 pages that follow that assumption are a little bogus at that point. And a lot of those, some of those algorithms worked in the real world, others didn't. But it was really difficult to know which ones did or didn't because it was hard to figure out how much of the behavior of the system that they were able to show using their model was actually dependent on some of these things. In the best case, when you're using a simulator, you actually, you get repeatability, and you can isolate a lot. You can build the simulator to be accurate enough to try to express what you're trying to show. And in the worst case, your simulator itself, either doesn't actually simulate enough about the system to provide real results, or in the worst case, it becomes a source of its own problems, right? Has bugs in it. I don't think this story is in the slide, but Margot, who we talked about a couple lectures ago, has a story about finding so she was working on this file system project. They had built this simulator to look at the performance of a file system that they were examining, and they had written a paper about this file system with data, right? Talking about how awesome it was. And then, unfortunately, she sat down with the simulator again, and she found a bug in it. The bug was kind of a problem, right? So the bug, if I remember correctly, was that when they evicted a block from the buffer cache, remember the memory cache? So you're trying to emulate a file system, you have to emulate the buffer cache. When they evicted a block from the buffer cache, they didn't actually simulate the time it would take to write it to disk, right? Or the disk activity that would create, right? Whoops. So yeah, it was the performance of a file system in which you could magically move blocks from the buffer cache to disk with no overhead, right? A little bit different than a normal file system would be. So they correct that bug, and wouldn't you know it, the number's a little bit different, right? So anyway, that's the kind of, unfortunately, she was in a position where she had to approach someone who was her sort of superior about this and be like, by the way. So what? And now that let's pretend that we can actually measure the system, right? Maybe build a simulator, maybe do some modeling. Now we have the next problem, which is how do I even compare things, right? What's the right? Someone brought this up before, and it's a great point. It matters. The performance of my system is very dependent on what I'm trying to do, right? So for example, disk drives, right? Can I establish something that says whether one disk drive is better than the other? Has a lot to do with what I want to do with it, right? Do scheduling algorithms, same thing, right? Scheduling algorithms that run on servers have one set of requirements. Those that run on interactive systems have a very different set, right? Page replacement, machine with a lot of memory, machine with not much, different workloads. Now, file systems, right? Now we have to compare features, not just performance. So, and you're back to this sort of thing, right? Which is, everybody's, two people can have, and a lot of times in computer science, when we have arguments about things, sometimes it's people arguing about two different things, right? It's like, this is better, right? And someone will say, no, this is better, but they're actually not, they would agree with each other if they could decide what they were talking about, right? So normally the way that we work around this is we develop benchmarks, right? So benchmarks are widely distributed tests that are sort of canonicized by the community and used to measure things about system performance, right? In general, you can break these down into 3 categories, right? You have micro benchmarks, and micro benchmarks do their best to try to isolate one part of the system, right? So for example, if I'm looking at a new architecture, I might care about, how efficient is its cache replacement, speed, right? And so I try to write a test to isolate that one specific part of the system. This is not trivial to do, right? Because again, I have to factor that aspect of the performance out of a lot of things, right? Macro benchmarks move up to sort of a higher level and measure lots of parts of the system. But the difference between these and application benchmarks, which focus on performance for a particular application, is the macro benchmarks try to still test things about the system that a lot of applications would use, right? So for example, if you looked at read or write performance of a file system, you could probably consider that to be a macro benchmark, right? I mean, read and writes involve a lot of different things that you could test individually using micro benchmarks, but it's still an aspect of performance that's relevant to a lot of other systems, right? And then again, application benchmarks you can think of it as taking an app, running it on the system, and trying to isolate its performance, right? And see, how well does this work for, so I can say things like, how well does the system work for database workloads, right? Database workloads have a particular set of characteristics, and I can, start to tell you how well my system will work for your app, right? So let's pick something like the virtual, let's do an example of coming up with some of these, right? So if I was trying to improve the virtual memory subsystem, right? That's just a random choice, right? Not at all related with what you guys are working on. What would be some micro benchmarks that I might look at? For example, one.
Keep blasting the heap.
What's that?
Keep allocating new data on the heap.
Well, okay, but tell me what aspect of the system would I be trying to measure, right? That's something that I could write a benchmark that does that. The question is, what would I be trying to actually measure? Gabrielle, do you have an idea?
How fast it is to allocate something.
Yeah. So how fast it is in this category, right? So keep going. Like one. Yeah, Doug.
Like core map functionality.
Like what? Yeah.
It takes like markup block is allocated in the format or something.
Yeah. How about how long does it take to allocate a page in the core map? Right? Very simple operation, right? Allocating the page of memory, something that operating systems have to do all the time, right? Even that, I mean, you could maybe say I could break that down into a couple of smaller pieces, but that's sufficiently level, right? How about time to handle a single page fault, right? So when a page fault happens, there's a code path that the system goes down. This may not be micro enough, right? It might be too macro because what if So what could potentially be a problem with this micro benchmark, right? As I said, I've got this micro benchmark that measures page fault time. What could be? Who can argue that this might not be? That I might need to break this down into a little bit of smaller pieces. Kevin, were you gonna?
I was going to say you must then get into like TLD functionality and other fun things.
Well, that's okay. Doug.
You have to go to the GLB and then you're going to have to track the kernel and then you're going to have to check all the page tables and the page table entries. And it's starting to get a bit bigger than really one functional unit. And then you also have to go out to the format if you have to.
So I guess if you're doing a page fault, you actually have to. But remember, there's a couple of different things that can, even if I distinguish TLB faults and page faults, there's a couple of different things that could happen during a page fault. Yeah. It might be on disk, right? That's going to include I/O now, so that's going to be a big cost. Where else could a page fault be?
It could be initialized when the page fault happens.
Yeah. So now I've got two different cases that are very two different cases that are very different. Yeah. Getting a page in from disk, right, involves I/O. Just adding a zero-fill page to the heap does not, right? I still might have to do some I/O to get something out of memory, but yeah, Gabriel. Yeah, there we go. I have a super fast page fault handler. It doesn't work, but it's awesome, right? It fails immediately. Yeah, I mean, if something's going to fail early, right? How about lookup time? How long does it take? I give you a virtual address, finding me the PTE for it. It's pretty micro, right? It's kind of nice. Now, your page replacement algorithms, how long do they take to actually choose a page to evict? Remember, I mean, the general theory when it comes to designing these algorithms is that implementing a smarter algorithm that takes 10 times as long is not a good choice, right? So how long does it take when I need to do this? A macro benchmark could be just aggregate. So we talked about page faults. If I ran a heavily loaded system, aggregate, the page fault rate that it can sustain, right? And this starts to combine all of these different things because a heavily loaded system that's sending a lot of pages back and forth to disk has to do all these things multiple times. It has to find pages, it has to choose pages to evict, it has to look up addresses as faults are happening, right? And then, there we go, triple sort, your awesome application benchmark, right? The only problem being, well, actually, here's a great question, right? So why might triple sort not be a fantastic benchmark for the VM system? Does anyone have triple sort working? No? Gabrielle?
Maybe because it's only doing one sort of activity.
Yeah, that's possible. So it turns out that triple sort actually also starts to depend on ways that people implement other parts of the system, like some of the system calls, right? So, for example, if your triple sort actually manages to simultaneously run 3 copies of sort, which is what it's supposed to do, right? Then it's possible it will take a long time because that creates a lot of memory pressure. However, there are some systems that we've observed where that's not how triple sort works, right? What triple sort actually does, right, is it runs 3 copies of sort sequentially, right? Because the second copy of sort, the exec doesn't actually finish until the first copy is basically done, right? So this is one of the reasons why there's this terrible test called parallel VM that's now in the tree, right? Because David realized that these triple tests actually in certain systems weren't stressing parallel use of the VM system by multiple processes because they were running sequentially. Yeah, there we go. Better. So now let's, when we think about these benchmarks, there's a number of different problems with deploying them. I mean, benchmarks are nice, right? Micro benchmarks, right? So it's possible that you've zeroed in on a part of your system that doesn't actually matter that much, right? And I think next time we're going to talk, on Monday, we'll talk a little bit about how to make sure that you have a big picture view when you're actually doing performance analysis, right? And there's some nice conceptual tools, right? But again, I mean, just, sometimes people, it's like, I found a great micro benchmark, right? Now I'm going to optimize it, right? Your system never even does that thing, right? So who cares? Macro benchmarks, we're back to this problem of, separating measurement from noise. So micro benchmarks can introduce so much different behavior that that can complicate your analysis quite a bit. And application benchmarks are always just on a per application basis, right? They might give you a very nice picture of how an application will perform, but a lot of systems are actually required to run multiple applications at once, right? It's hard to believe. Actually, there are when we talk about virtualization, one of the early uses of virtualization was to work around the fact that there were vendors who would sell software to clients, but like a database server, right? So you buy a database server from XXX company, and they say, okay, I've given you this cool piece of software, you have a license, whatever. There's only one caveat. We will not provide support for you or help you with your performance problems unless our database server is the only application running on your system. The only one, right? So now I've got this machine that's sitting in my machine room. All it does is run this one stupid application, right? And it might not be very busy running that one application, right? But if I put it, hey, you cannot run a web server on that machine, right? Or we will not help you with your problems, right? So, to some degree, that's one way that companies worked around this, right? It wasn't a great way. So one of the bigger, sort of more systemic problems with benchmarking in practice is that people choose, this is the ends justify the means sort of approach to benchmarking, right? If I don't like the results, don't improve the system, just find a different benchmark, right? So until, how many people remember when Apple didn't have x86 processors on their machines? Oh yeah, the good old days, right? So for years, Apple ran these like glossy ads in all of these magazines being like, our processors are so much faster than the x86 ones, right? And you know, who knows? Were they? It was hard to tell, right? It was lots of apples and oranges. And then suddenly they were like, whatever. they were so much faster that we decided to use the x86 ones instead, right? Because we just felt like we were getting too far ahead, right? Like we had to handicap ourselves with everybody else. So anyway, I'm sure there were other reasons for that. But the point was that for years and years they made these claims. You know, they'd show you, oh, on this particular benchmark, like if you're running, you know, 6 copies of video decoding, like this is an awesome system. So it's not clear exactly how useful some of that stuff was, right? So, I mean, this is kind of like the worst of this, right? A little bit better is you choose a benchmark and then you just optimize the crap out of it, right? In the meantime, who knows if the rest of the system is really getting better, or if you're just building a whole system that's good at the benchmark, right? It may be getting worse at other things. And then this isn't just all, again, human folly and the general malaise of the human condition, right? There's some fundamental realities to this, right? And part of the problem is that the most useful system I can build does a lot of things well, right? But the fastest system is good at doing one thing, right? And sort of working out the tension between these two goals has been something that's been going on in the computer systems community for a long time, right? We talked last time about how these, modern mobile systems have like 6 or 7 or 8 different cores on them, right? That is this, right? That is the fact that, you know what? It's faster to do MP3 coding or MP3 decoding on a dedicated core. It also consumes less energy, right? So this sort of tension is something that's still playing out. So we've talked a lot about some of the problems, right? So I'll talk a little bit about how to use benchmarks effectively, right? One thing to do is to have a specific goal in mind, right? That's more specific than I want to make this faster, right? What are you actually trying to accomplish, right? This helps you choose both your measurement techniques and the benchmarks, right? When you're using models and simulations, those need to be validated, right? So for example, can you convince yourself that the simulator behaves in the same way as the real system? Is the performance of the simulator similar to the real system? If it's not, then it's not a very good simulator, I would argue. And good performance testing and benchmarking uses these tools carefully, right? And as appropriate, right? Like if I've convinced you of nothing else today, it's that there's no silver bullet to solving this problem, right? And that a good solution involves a variety of these techniques. Right, and again, so sometimes you do these things in layers, right? So you start and you say, okay, I can convince myself analytically in a perfect world that this is a good idea, right? This is a good approach. Then I'll build a simulator, because that's faster potentially than integrating it into a real system, and get that to work. And then, assuming the simulator shows promising results, then I'll try to implement it in a real system and get some real results. Right, so this could be a good approach. All right, so on Monday, we actually will talk about statistics, Amdahl's law, and then what to do, right? So how do you, the analysis tools you use to interpret results, how to figure out what to work on, and something about what to do, all right? All right, have a great weekend. I will see you on Monday.